Hello and welcome. Today we're going to be doing an example solution to the equilibrium wave equation under an applied load. So let's write down what we're talking about here. We're going to talk about the wave equation, and that's going to be rho times UTT is equal to T UXX plus some applied pressure that we're going to put on our thing. And U, of course, is going to be the vertical height to a stretch cable under tension T with mass density rho and applied pressure F. Okay, so and of course we have a string that's stretched 0 to, we'll call it L, and we'll say that it's anchored at the endpoints to 0 height. So the picture we have here is there is 0 and there is L, and then we have some sort of pressure, and that could be down here, could be up here like that, and then up like this, like that, and you could get some that your U of X will look something like this due to the pressure applied to it, right? So the question is, what does this string look like when you're given an applied pressure? So what we're going to do, of course, is we're going to be looking at a no motion situation. So we're going to say UTT is equal to 0. Okay, so that means that rho, this parameter, is actually irrelevant unless it shows up in some other aspect of what we're doing here. So the applied pressure, that's going to be F of X. That's going to be it's sort of a force, but it's a force per unit length. So we call it a pressure. And of course we have some tension on the string. Okay, so what we want to do now is I'm going to give you a very specific problem. Okay, we're going to talk about this one. So X is going to be on the domain 0 to 2. And the applied pressure, this is going to be an interesting one, is going to be negative K times H of X minus 1. So this is what we call the Heaviside, I should capitalize it because it's a person's name, step function. And this parameter here, K, that's just going to be a parameter. We'll say K is positive, and that's basically just the strength of the pressure. And the fact that it's negative, that means it's downward. It's a downward force or pressure, okay? So now we can set up our problem as so. So we're going to have a T UXX minus K H of X minus 1. So the Heaviside step function, it's probably worthwhile to actually graph this thing. What does this look like? So if this is an axis here, and that's going to be 0, and that's going to be 2, what we're saying here is this function, and I'll draw the Heaviside in blue, jumps up to 1 at x equals 1, like that. So this is H of X minus 1. So what we're doing basically is we're applying a uniform pressure on the right half of the cable. The left half, we're going to have nothing. All right, so we want to know what's going to happen to this. What is going to be the deflection of the string? and we're going to say rho UTT. We know that's equal to 0. So what we have here is this equation. We have a differential equation here, set equal to 0. Okay. We also have boundary conditions. U of 0 is equal to U at 2 is equal to 0. Okay. So the big question then is, of course, what is U of x? What does the cable deflection look like? All right. Especially as we want to look at maybe, how does it depend on, we want to know how does it depend on the tension and the pressure dependence. Okay, so let's look at that. So we're going to have to know a few facts here that's going to help us a little bit. So here's some important facts to understand. I shouldn't say understand. We'll just say important facts to help calculate U of x. So the important fact I want to bring up here is actually we're going to do this with, it's better to do it with definite integrals. So it's better to do it with definite integrals, okay? So we're going to, rather than indefinite integrals. And so we have to note that if I take the integral starting at 0, because that's the beginning of the domain, and I'm going to go up to x, right? And if I have h, I'm going to integrate over our Heaviside step function, and I use a dummy variable inside the integral. That's going to be equal to h of x minus 1 times x minus 1. And again, I think the way you want to think about this is remember that what we have here is a step function, like this, right? And now when I pick a certain x here, what's the area under the curve here? But then if I move x here, still 0 area. But then when I move my x here, I see the area under the curve is going to grow it grows linearly. So the idea here is if I were to draw another one of these axes here, what does the integral here? What does this graph look like? It's going to be 0 here, and that right at 1, it'll take off and grow linearly like this. All right. Another important fact that we want to look at is, okay, if I take this function, we'll call it f of x now. And now if I take the integral from 0 to x of f of s ds, what's that going to look like? Well, you imagine it's going to look like a parabola. And of course, it's going to be equal to h of x minus 1 times x minus 1 quantity squared over 2. And the idea here is if I take an x here, again we have 0 area, x there, also 0. But the minute I bring my x over here, we see we clearly are getting an area under the curve there, and that's gonna, the area under the curve grows quadratically. Okay, it's going to grow quadratically as you go further and further along. You'll see that the area under the curve here will just keep growing now as a function of x squared. But it's going to start at x equals 1. There'll be 0 area under the curve beforehand. Okay, so that helps us. It's really difficult. Students have a lot of trouble typically integrating piecewise functions. The fact that you have to keep track of when things turn on and off. So I thought we'd just get this out of the way at the beginning of our video here so that when we get to solving the problem, we don't get confused. So we can use these results. All right, so let's go back up to our problem here. Here's our problem. I'm going to write this on the next page and we're going to get going. So what we have here is, we can write it out now like as follows. We have T UXX is equal now, and we're going to move my forcing function over to the other side. It's going to become a positive K H of X minus 1, like that. And then I might as well just erase the T and bring it over there. All right, so now I have a K over T. Again, that's just going to be some constant. All right, so now what I'm going to do is I'm going to be integrating both sides. So I'm going to integrate from 0 up to x of UXX, and then I'm going to evaluate it at our dummy variable, like that. And of course, I can take the antiderivative, like so, because again, this is a definite integral, okay? The question is then, we don't know what that is, right? This is right here is a function, but that is a constant. But then we can integrate this 0 to x of k over t h of s minus 1 ds, and we can get the result that we just computed over there just a second ago. All right, that's that linear growth that happens after the Heaviside turns on at x equals 1. All right, so what we can do then is move this over. We have the function here, and we have kt h of x minus 1 times x minus 1. Now it's going to be plus ux of 0. So this constant here actually behaves, this is essentially a constant of integration. Okay, and what we're going to do is we're going to determine it via boundary conditions. But we're going to leave it in the problem as a constant right now. We don't have to worry too much about that. The next step, of course, is to integrate again. Oh, I have to undo that. So now we've anti-differentiated one more time, and we got u of x minus u of 0 is now equal to, again, we're going to do the integral as a definite integral. So now we're going to use our dummy variable. And we're going to integrate this again, and we're going to end up with k over t h of x minus 1 times x minus 1 quantity squared over 2. But we have one more thing there. We had to integrate this one, so we're going to put that there as a plus the integral. Well, I don't need to write the integral. I just need, because this is a constant, I'll just leave it there times x. Okay? We know that's what it's going to result to, so we'll write that u of x 0 is x. Again, we don't know what that is yet. That's just a constant hanging around. Okay, it's not a function of x, it's just a number. All right, so like before, we can also identify this one. We know what that is. We know from the boundary condition that that's going to be equal to 0. Okay, so we can get rid of that right away, and that's nice. I'll move this up a little bit. So we have our u of x is going to equal k times t times h of x minus 1 times this quadratic plus ux at 0 times x. So what we want to do, of course, is now use the boundary conditions. So we know u at 0. If I write this there, that's going to be equal to 0, right? Because, first off, the Heaviside is 0 for any negative input, right? And this is going to be 0 as well, so that creates a 0 there. So this satisfies the first boundary condition. Cool. All right, so the next step we got to do is now look at the other end. So we're going to look at u of 2, and that's going to be k times t times h of 2 minus 1, which is 1, times 2 minus 1, which is going to be 1 squared over 2, okay, plus ux of 0 times 2, and that's going to be equal to 0 because that's what the boundary condition says. All right, now here's where we need to make a really important insight here is that this, of course, is going to be 1 now, okay? So what we have here is, if we put this all together, we're going to get k over t times 1/2, right? Plus ux at 0, the thing that we don't know yet. We don't know what that is. Times 2 is equal to 0. Of course, we can move these things around and find that ux at 0, this number, is going to be equal to k over t times 4. Oh, sorry, it has to be minus there. Cool. All right, so we have that piece of the puzzle. Now let's, I think we have the full answer then. So we have u of x is equal to k minus k over t times 4 x plus k over t times h of x minus 1 times x minus 1 quantity squared over 2. And this is our final answer. Okay, so I'd like to take that, copy it, and now I'm going to move it over to the next page. There we go. That's our final answer. So I think now it's worth, we need to plot this. We need to come up with what our understanding of it. So here's what we know so far. We have an applied force. So I'll plot the applied force above it. And we know the applied force is 0 until you get to 1, and then it drops down to negative k. So this is our applied force. We're basically pushing down on half this cable. So we expect that there's going to be more deflection of the cable on the right-hand side as we get out to 2. Okay, so now if we look at u, we expect that the deflection is going to be negative, that we're going to have negative values for the cable because we're pushing down on it. But we also know that it's 0 at the boundaries, okay? The first thing here, what I'd like to look at here is probably better to actually represent this as a piecewise function. So we see on the first half, so for x in the range 0 all the way up to 1, remember that the Heaviside is completely turned off. That whole quadratic term has just disappeared. I think that's what's difficult for students to see, is you have to kind of think of those Heavisides as basically turning on and turning off parts of a function depending on what the x value is. So what we're going to get is basically negative k t over 4x. All right, so this is going to, of course, be basically a linear function. All right, and it starts like this, and it goes down like that to some point, and then we have at x equals 1, something weird is going to happen. Now, and then here we're going to have negative k over t times 4x plus k over t times the quadratic. And this is for x on the 1 to 2 range. All right, so I didn't have to write the Heaviside there because remember that Heaviside function is 1, so I can just write it like this, right? So clearly that right here is a quadratic. And we know the function is continuous, so the function is going to start there. So what I really want to know actually is basically what is the slope of u at x equals 1 coming from the positive side, and x is equal to 2 coming from the negative side. So if I look at x at ux, what I can write there is that's going to be negative k over t times 4 plus 2k over, oh, sorry, I should undo that. We're going to say it's just going to be k over t times x minus 1 to the first power. So that's what the slope is. So ux at 1 is going to be equal to negative K over T times 4. So what we're seeing here is that basically, if I look at that right there, I'll cover it in red. We know we're going to have a slope that's actually continuous with the slope on the left half of the cable. So the slope is still going to be the same there. But then it's going to slowly rise like that. And at some point it's going to turn positive. Actually, let's find that point where it turns positive. Where is u of x equal to 0? We can find that pretty easily, I'm sure. So it's going to be equal to kt x minus 1 is equal to kt over 4. All those cancel. We're going to get x minus 1 is equal to 1/4, otherwise known as x is equal to 1 1/4. So that's going to be at the point there, about 1 1/4 coming down. So at that point, what we're going to have there is a 0 slope, and then it's going to start coming back up, and it should go positive, and it's going to run right into there. So there at ux at 2, we're clearly going to get, if we plug it into here, we're going to get 3/4 K over T is the value there. So it's going to be, of course, a positive slope at that point right there. All right, so here we have that 0 slope at 1 1/4. So that's what the deflection looks like from that constant or that uniform pressure on the right half of the cable and 0 pressure on the left. You get this funky looking solution. So you can imagine that this is an incredibly useful, the wave equation in equilibrium is a really important tool when you're talking about elastic objects, like cables, and you're applying forces or pressures to them, and you want to know what the deflection looks like. So this, of course, is a really useful differential equation. It's no longer a partial differential equation because you've set the time derivatives equal to 0. But it does tell you that equilibrium deflection of the cable under a specific load that you can apply. So, of course, the applications for this are infinite in the realm of engineering or science or anything like that involving elastic elements like cables with applied loads. So I hope you enjoyed this video. I'll see you in the next.